1. 2 lattices. 1 hidden structure. In the previous chapter, we discovered something remarkable. Numbers written as the sum of 4 squares can form beautiful structures in 4-dimensional space. But now we are going to look at those structures from a different perspective. Consider the Hurwitz integers. They are points in 4-dimensional space whose coordinates are either all integers or all half integers. Together, these points form a remarkably symmetric 4-dimensional lattice. Now consider another familiar object, the D4 lattice. Its points have integer coordinates, but with one additional condition. The sum of the 4 coordinates must be even. At first glance, these two lattices seem quite different. The Hurwitz integers contain both integer and half-integer points. The D4 lattice contains only integer points. Even their smallest non-zero vectors have different lengths. For the Hurwitz lattice, the minimum squared norm is 1. For D4, the minimum squared norm is 2. So these do not appear to be the same lattice. And yet, there is a remarkable connection between them. A precise transformation can take every point of the Hurwitz lattice to a point of D4. Not approximately, not just for a few special points, but for the entire infinite lattice. And this transformation preserves the essential geometry while changing the scale. In other words, 2 apparently different 4-dimensional lattices are secretly describing the same underlying structure in 2 different coordinate languages. Our goal in this chapter is to uncover that bridge. We will see how 4-square arithmetic leads naturally to the 2 lattices, how parity divides them into 4 related families, and how a simple matrix reveals an exact bijection between them. But there is an even deeper question waiting for us. If the 2 lattices are so closely related geometrically, does the relationship also preserve multiplication? That question will eventually lead us from geometry to algebra. For now, we begin with the 2 lattices themselves. 2 different descriptions. 1 hidden structure. 2. The 4-square fingerprint. We have seen 2 very different 4-dimensional lattices, but before we try to connect them, we need to return to the arithmetic that generated our shells in the first place. Take any positive integer, n. Ask a simple question. Can it be written as the sum of 4 squares? N equals w squared plus x squared plus y squared plus z squared. Every solution gives us a 4-dimensional integer point, and every such point lies on the shell of squared norm, n. This is the arithmetic fingerprint of the shell. For n equals 1, we have 1 equals 1 squared plus 0 squared plus 0 squared plus 0 squared. So we obtain points of the form plus or minus 1, 0, 0, 0, together with their coordinate permutations. For n equals 2, 2 equals 1 squared plus 1 squared plus 0 squared plus 0 squared. Now 2 coordinates are non-zero. For n equals 3, 3 equals 1 squared plus 1 squared plus 1 squared plus 0 squared. For n equals 4, something more interesting happens. We have 4 equals 2 squared plus 0 squared plus 0 squared plus 0 squared. But we also have 4 equals 1 squared plus 1 squared plus 1 squared plus 1 squared. Already, the same number can produce different geometric patterns. Continue. 5 equals 2 squared plus 1 squared plus 0 squared plus 0 squared. 6 equals 2 squared plus 1 squared plus 1 squared plus 0 squared. 7 equals 2 squared plus 1 squared plus 1 squared plus 1 squared. And even 14 equals 3 squared plus 2 squared plus 1 squared plus 0 squared. Each number leaves behind its own geometric fingerprint. The important point is that we are not choosing these points arbitrarily. They are dictated by the arithmetic. A number determines which coordinate patterns are possible. Those patterns generate symmetry orbits, and the orbits generate the complete integer shell. This is the connection we will need. The shell is simultaneously a geometric object and an arithmetic object. Its points can be viewed as locations in four-dimensional space, or they can be viewed as solutions to a four-square equation. The two descriptions contain the same information. And this is precisely why the decomposition of an integer into four squares matters so much. Because once we understand the arithmetic structure of the shells, we can begin to ask where those points sit inside the D4 lattice. That is where the hidden correspondence begins to emerge. But there is still something missing. The integer points are only part of the Hurwitz story. For certain values of n, another shell appears, one made from half-integer coordinates. And understanding where that second shell comes from will be our next step. Three, the hidden half-integer shell. In the previous scene, we followed the integer points. Each one came directly from a representation of a number as four squares. But the Hurwitz lattice contains something more, not just integer points, but half-integer points as well. Where do they come from? The answer is hidden inside the same four-square equation. But this time, we change the question slightly. Instead of solving n equals w squared plus x squared plus y squared plus z squared, we consider 4, n equals u squared plus v squared plus s squared plus t squared, with one important restriction. All four coordinates must be odd. Why? Because an odd square is always congruent to 1 modulo 4. So 4 odd squares always add to 1 plus 1 plus 1 plus 1. This makes the construction possible. Now comes the remarkable step. Take one of these all-odd solutions and divide every coordinate by 2. For example, an odd vector, 1, 1, 1, 1, becomes 1/2, 1/2, 1/2, 1/2. We have just produced a Hurwitz integer of the half-integer type. The arithmetic has generated a completely different-looking family of points. For n equals 1, we obtain the half-vector pattern, 1/2, 1/2, 1/2, 1/2. For n equals 3, another family appears. Then again for n equals 5, and again for n equals 7. A clear pattern is beginning to emerge. Odd values of n can produce a half-integer shell. Even values cannot. This is not an arbitrary rule. It follows directly from parity. If n is even, then 4n. But 4 odd squares are each congruent to 1 modulo 8. Their sum is therefore 1 plus 1 plus 1 plus 1 equals 4. So the required equation cannot hold. The half-integer shell is therefore controlled entirely by parity. And now the picture becomes much richer. Every Hurwitz shell has 2 possible sources. The first is the ordinary integer 4-square shell. The second is the half-integer shell, obtained from all odd representations of 4n. So we can think of the Hurwitz shell as the union of 2 arithmetic worlds. Integer shell plus half. Integer shell equals Hurwitz. Shell, the first, comes directly from ww squared plus x squared plus y squared plus z squared equals n. The second comes from u squared plus v squared plus s squared plus t squared equals 4n, followed by division by 2. And together, they form the complete Hurwitz shell. This is an important turning point. The half-integer points are not something added by hand. They are not a separate geometric construction. They emerge naturally from the same arithmetic. Numbers generate the integer points. Parity generates the half-integer companions. And together, they reveal the full structure of the Hurwitz lattice. But now another question appears. If the integer shell does not always belong to D4, and the Hurwitz lattice contains these 2 different types of points, Then where exactly does D4 enter the picture? The answer is parity. Four, parity splits the lattice. In the previous scene, we discovered that the Hurwitz shell contains two kinds of points, integer points and half-integer points. We also discovered something important about the integer points. They have a hidden property. Their four coordinates can be added together, and that sum has a parity. It is either even or odd. For example, consider 1, 1, 0, 0. Its coordinate sum is 1 plus 1 plus 0 plus 0 equals 2. Even. Now consider 1, 0, 0, 0. Its coordinate sum is 1. Odd. So the integer points naturally divide into two families, the even sum points and the odd sum points. And this is where D4 enters our story. The D4 lattice is precisely the set of integer four-dimensional points whose coordinate sum is even. So we can write D4 equals A, B, C, D, belonging to Z to the power 4, such that a plus B plus C plus D is even. Suddenly, the connection becomes visible. Part of the Hurwitz lattice is already D4. The integer Hurwitz points with even coordinate sum belong to D4. What about the other integer points? Those with odd coordinate sum? They form the complementary parity class. Take 1, 0, 0, 0. Its coordinate sum is odd. Add an even sum, D4 vector to it. The parity changes from even to odd. So the odd sum points form a translated copy of D4. We can think of the two integer families as D4 and D4 plus 1, 0, 0, 0. One has even coordinate sum. The other has odd coordinate sum. And together, they contain every integer point. This is the first appearance of the Cosets structure that will become so important later. But remember what we saw in the previous scene. The Hurwitz lattice does not contain only integer points. It also contains half-integer points. Those half-integer points have their own structure. So the complete Hurwitz lattice is beginning to separate into four related families. Two are integer families, D4 and its odd sum companion, and two more arise from the half-integer points. The four families are not unrelated. They are different cosets of the same underlying lattice structure. This is a remarkable simplification. What first looked like a complicated mixture of integers and half-integers can be organized into four clean pieces. And parity tells us how the first two pieces fit together. There is an even deeper consequence. Look back at the shells we generated earlier. For some values of n, the integer shell lies entirely in D4. For others, the integer shell lies in the odd sum coset. And for still others, the shell contains points from both parity classes. The arithmetic of the four-square representation is therefore telling us something about the lattice cosets. Numbers, coordinate patterns, parity, and lattice structure are all beginning to fit together. But there is still a problem. The Hurwitz lattice and D4 do not have the same minimum norm. The shortest Hurwitz vectors have squared norm 1. The shortest D4 vectors have squared norm 2. So even though parity has revealed a direct connection, the two lattices are not simply identical. Something must transform one into the other. We now know what we are looking for. Not just a correspondence between a few special points, but a transformation that organizes the entire lattice. A transformation that takes the four Hurwitz cosets and maps them into the appropriate D4 structure. That transformation will be our bridge, and in the next scene, we will see the four-coset picture in full. Five. Four cosets, one lattice. In the previous scene, Parity revealed something remarkable. The integer points of the Hurwitz lattice are not one undifferentiated collection. They divide naturally into two families, the even sum points and the odd sum points. The even sum points are exactly the D4 lattice. The odd sum points form its complementary coset. So already, the integer part of the Hurwitz lattice can be written as two pieces. But we are still missing the half-integer points. And these are not an unrelated collection. They fit into the same picture. Remember what we discovered earlier. A Hurwitz integer is either entirely integral or entirely half-integral. So the Hurwitz lattice has two coordinate types, and the integer type has two parity classes. This strongly suggests a four-part structure: two integer cosets and two half-integer cosets. Let us make that structure explicit. The first coset is simply D4. These are the integer vectors whose coordinate sum is even. The second is obtained by translating D4 by an odd integer vector. For example, D4 plus 1, 0, 0, 0. Every vector in this translated set has odd coordinate sum. Together, these two cosets contain all integer points. Now turn to the half-integer points. Choose the half-integer vector omega equals with 1 over 2, 1 over 2, 1 over 2, and 1 over 2. Translate D4 by this vector. We obtain D4 plus omega. This gives one family of half-integer points, but there is another half-integer family. For example, translate by omega plus 1, 0, 0, 0. This gives D4 plus omega plus 1, 0, 0, 0. And now the entire Hurwitz lattice can be organized into four cosets: D4, D4 plus 1, 0, 0, 0, D4 plus omega, and D4 plus omega plus 1, 0, 0, 0. Four families. One lattice. This is the structure that was hidden inside the mixture of integer and half-integer coordinates. And notice what has happened. The distinction between integers and half-integers gives us one division. Parity gives us another. Together they produce four classes. We can visualize the structure as a four-way decomposition. H is equal with the union of four classes: D, 4, D, 4 plus 1, 0, 0, 0, D, 4 plus omega, and D, 4 plus omega, plus 1, 0, 0, 0. This is more than a convenient way of sorting points. It tells us that the complicated-looking Hurwitz lattice can be reconstructed from a single D4 lattice, together with three translations. The integer points occupy two of the four classes. The half-integer points occupy the other two, and the four classes together give every Hurwitz integer. This also explains something we saw in the earlier shell calculations. Different shells appear to behave differently. For one value of n, the points may lie entirely in D4. For another, they may be distributed across two cosets. For half-integer shells, the points occupy the corresponding half-integer classes. The apparent complexity of the shells is therefore not random. It is controlled by the Coset structure. Arithmetic determines the shell. Parity determines its integer coset. And the integer versus half-integer distinction determines which pair of cosets we are looking at. Three different descriptions, but one underlying organization. This gives us a much better way to think about the relationship between H and D4. We should no longer think of them as two unrelated point sets. Instead, think of D4 as the underlying lattice framework, and H as four translated copies of that framework. The two lattices have different coordinate descriptions, but their arithmetic structures are beginning to look remarkably compatible. There is only one major question left. Can we find a single transformation that takes this entire four-coset structure of H into D4? Not just one shell. Not just the 24 vertices, every point. And if such a transformation exists, does it preserve length? Does it preserve the lattice? And exactly how does it change the norm? The next scene will answer those questions. We are finally ready to reveal the bridge.